Welcome back. We continue with object-oriented applications testing. In the last two lectures of week 10 that we did, we looked at some properties related to object-oriented applications that were useful for us from the testing point of view, and also looked at mutation operators for integration testing with object-oriented features in mind. We continue with object-oriented applications testing, but we look at other features in the next two lectures, this one and the next one. So this is a summary of what we're going to do. We looked at features of object-oriented software already, and we'll do some more today, specific to what we need for the latter modules of this week. I'll give you a cataloging of faults, anomalies, or errors that occur typically in object-oriented software. I call it a catalog because it's a list, and not an exhaustive list, but a reasonably long list of faults that occur because of object-oriented features. Then we look at two more aspects related to testing of object-oriented software. One is what we call a yo-yo graph. It represents call graphs, but for method calls that are specific to object-oriented applications with all the features that we saw in the first lecture of this week. So it's a unique graph that represents calls that can happen, that will happen, all kinds of calls across a class inheritance hierarchy, and calls bounce up and down, having the effect of a yo-yo toy. So that's the name yo-yo graph. We will also look at call coverage specific to object-oriented applications called object-oriented call coverage. These are call interfaces, but they look different from normal call interfaces. So we'll have to rework with our last definitions, first uses, coupling variables, and then define coverage criteria. So this slide deck is a summary of two lectures, this one and the next one. So we will get started with object-oriented applications. As I told you, we've seen common object-oriented terms. Now, like all other programs that follow object-oriented language, Java programs can be tested at the unit level within a method, or even for C# or any other object-oriented programming language, there will always be methods, functions, and procedures that need to be tested at the unit level. Nothing that we see specifically this week is going to talk about testing at that unit level, because at the unit level, we may not use too many object-oriented features. So testing that can be done by normal testing, using any of the criteria that you've learned till now in the course. Use control flow graphs or data flow graphs, or logical predicates if you have a rich collection of predicates within your method, or symbolic execution, or even mutation testing if you suspect a lot of low-level errors. So unit level testing can be done. So we're not going to see any exclusive methods to do unit level testing specific to object-oriented applications. We already saw mutation operators for object-oriented integration testing. So now the focus is going to be other aspects of object-oriented integration. So testing of the software, basically now we're going to concentrate on faults that occur because of certain niche OO features. One is that of abstraction, because we're going to do integration of components as a part of object-oriented programs. So abstraction will focus on how the components are connected to each other. We are going to focus on classes, inheritance of classes, and polymorphic methods that are owned by various classes, because they define new connections which are very different from ordinary functions that you will see in other languages. So testing is going to focus on integration testing. We've already seen mutation operators for integration testing, but we're going to see now testing, other aspects of testing that focuses on these features. Just another recap of some more object-oriented terms that we will need to see us through these remaining two lectures. This is, we know, why do we use classes in object-oriented programming language? Because they represent data abstraction. It's a convenient way of putting together things that we need to in one place, things that handle data in one place that is abstracted out. In addition, we have class inheritance, polymorphic methods, and dynamic binding. They also support abstraction. A new type can be created by inheritance, and they become descendants of an existing type. When it comes to a parent class and a child class, you can define two notions. One is that of extension, one is that of a refinement. We say a child class extends its parent's class if it introduces a new method name and does not override any of the methods in the parent or the ancestor. On the other hand, a child class refines a parent class if it provides new behavior that was not present in the overridden method, does not call the overridden method, and its behavior is still semantically, meaningfully consistent with that of the overridden method. And when it comes to class inheritance, we popularly consider two types of inheritance in object-oriented programming languages. One is called subtype inheritance, the other one is subclass inheritance. Subtype inheritance is famously called substitution principle, was introduced by Professor Barbara Liskov. Interestingly, Professor Barbara Liskov got the Turing Award for her work on this subtype inheritance. Turing Award is the highest award in computer science. So what does subtype inheritance or substitution principle says? It says if a class B uses subtype inheritance from class A, it's possible to freely substitute any instance of B for A and still satisfy an arbitrary client for A. In which case, we say the class B has what we call is-a, within quotes, is-a relationship with class A. The other is subclass inheritance. This allows the child or the descendant classes to reuse methods, to reuse variables from the parent or ancestor classes, and they need not ensure that the instances of the descendants meet the specifications of the ancestor. So a method is polymorphic, we've already seen. Let's say we have two classes, class B inherits from class A, and both A and B define a particular method, let's say M. Then M becomes a polymorphic method. So now let's take an object X, and suppose the object X is declared to be of type A. Then when the code associated with this class A executes, during execution, the actual type of the object can be A, or it can be the type of the child class B. The version that executes depends on the current actual type of the object. It's very difficult to determine it statically in object-oriented programming languages. For those of you who are familiar with Java programming, will immediately be able to relate to this. And so we don't know which method will execute because class A has its own method, class B has its own method M, same name. And so either A's version of M or B's version of M can execute. So we put together all these things and say it's a collection of methods that can execute. That collection is called the polymorphic call set. Polymorphic call set represents all the methods from the parent class, the inherited child class with the same name, same signatures, polymorphic methods that can execute. Any of these methods can be called by another method in the call graph. And we don't know which version of method, A's version or B's version will be called, and we can't determine this statically in the sense that this happens when the program executes. We have to wait for the program to execute. So when we consider classes in object-oriented testing, right, that's considered as the highest level. Of course, a method is the lowest level of unit testing, but class is considered the basic unit in the sense the highest level of unit testing. So it has several concepts within it. So when I test a particular class or a set of classes, I can segregate it into 4 different levels. One is intra method. When we use the word intra, we say within. Right? So intra method is within a method. So that is traditional good old unit testing. Like I told you in the beginning of this lecture, test it in any way that is convenient for you. Any of the unit testing methodologies that we've learned till now. So that's our good old unit testing. We don't have to redo it once again. The next is inter-method testing. Let's take a class and let's take multiple methods, one or more methods within a class, 2 or more methods within a class. And they are tested to work to see how they work together within a class. So this could be thought of as module testing or some kind of simpler integration testing within a class. The other is intra-class testing. This is the same as inter-method testing. Basically, second and the third one here are more or less the same. In both cases, you construct tests within a class, within a single class. by using method calls that happen within that class. The fourth one is the most complex one, inter-class testing. So more than one class. It could be a parent class and an ancestor class and its children class, descendant classes, right? Or two separate classes, whatever it is. More than one class is tested at the same time, putting together all the call interfaces to see how they interact. So this is the most complex version of integration testing that you can think of. And this is where all the new problems related to object-oriented features come into play. So what are all the problems that happen? So we know that a class encapsulates state information. Every program has a set of variables, and the values associated with our variables constitute the state of a program. So the same holds for object-oriented programs, and we assume that class contains state information that is given by a set of state variables, which are the variables present in the program. The behaviors of the class are implemented by the methods that use the variables, read from the values of the variables, write onto or update the values of the variables. One or more methods that are owned by the class can do this. Interactions between the various classes and methods can occur in the presence of all these features: class inheritance, polymorphic methods, dynamic binding. So they're complex and they're very difficult to visualize. I cannot neatly draw a call graph because I don't know which version of the polymorphic method is going to run. So we'll see some examples to illustrate what is the actual difficulty. So on the left here of this top left, you see this picture here, this diagram. I hope you're comfortable with reading this simple class diagram. So I'll read it out for you. This picture says that there are three classes. The topmost box here gives the name of the class. W is one class, V is one class, X is another class. This arrow, V and X are at a lower hierarchy, W is at the top, and these lines that connect W and V indicate that classes V and X, both of them, extend the class W. In addition to that, W has a variable V, and X has W has a variable small v, and class capital V has a variable X. The minus sign before them, as we saw earlier, indicates that these variables are private to that class. And then there are a set of methods that are owned by the class. Class W owns a method M. It also owns another method N. And these plus attributes indicate that they are non-private. Method M is also owned by class V, and because V extends W, class V extends class W, the method M in V overrides the methods here. Similarly, class X extends class W, and class X also owns the methods M and N, and these two methods override the corresponding two methods of the class W. So that's what this picture says. There are three classes, W, V, and X. Classes V and X extend class W. The three classes have some variables that are private to them, indicated by the minus sign prefixing the variable name. The classes also own some methods, M, N, across a subset of them. And whenever the same name is used in another child class that extends the parent class, you say that particular method is overrides the corresponding method in the parent class. So now look at the code on the right hand side. It's a small snippet again, a fragment of the code. The full code is not given. So let's say there is a function f which takes as argument a Boolean value b. And here at line 3, the declared type of object O is W, class W. Now the code runs, something happens at line 4. I've put it as ... because I don't want to detail out. Some code executes. Let's focus on this if statement. Now if B. So if this B variable tests true, then line 6 says O is equal to new of V. And if this B variable tests false, then line 8 executes and that says O is new of W. So actually at line 3, the declared type of object O is W. But now by the time the code finishes executing this if statement and comes to line 10, the actual type of this object O can be V or W based on whether the Boolean variable B tested true or false. And we can't determine this statically because it's completely dictated by whether the Boolean variable B tests true or whether B tests false. Any of these can be assigned. So these methods can get overridden. If V's version runs, then M will start running. So these kinds of issues are difficult to determine statically. Another example, this is a slightly long one. On the left, you again have a class inheritance hierarchy. This time there are 3 classes. Their names are A, B, and C. Class A has 4 variables, T, U, V, and W, prefixed by a hash. What does the hash prefix say? You might want to think for yourself for a minute. And then class A also has 6 methods, D, G, H, I, J, and L. Class B has a variable X and 3 methods, H, I, and K. And if you see, the H and I here are connected to the H and I methods of J. What does this mean? This means that the method H of B overrides the method H of A. Similarly, the method I of B overrides the method I of A. In addition to that, B has its own new method K. C is another child class. Class C has methods I, J, and L. Method I of class C overrides method I of class B. Method J of class C overrides method J of class A. That's where this arrow points to. And there is a method L of class C which overrides method L of class A. I've just walked through this class inheritance diagram for you. This slide explains that. It says there is a root class A. It has 4 state variables, T, U, V, and W, and 6 methods, G to L. It also has 2 descendants, B and C. Assume that the methods of A are called in sequence. That is, method to start with, method D runs, D calls G, which in turn calls H, which in turn calls I, and so on. So they are called in sequence. The state variables of A are protected. This hash symbol says they are protected, which means they are available to the descendant classes B and C. B declares another state variable and 3 methods. We saw that. C declares 3 methods. And this is the part I read out to you from the figure. The method H of B overrides the method H of A, method I of B overrides the method I of A, and so on. That's what is written here. Now, look at the table on the right hand side. So the first column in the table talks about all the methods that are available. The class A has actually 6 methods, but let's say 4 of those methods are important for us, for our current focus. Class B, we consider 2 of those methods. How do you read this? A :H, you say the method H as owned by the class A. Method I of class A, method J of class A. Similarly, B :H indicates method H of class B. Similarly, method I of class B, method I of class C, and so on. The second column and the third column talks about definitions and uses of some of the variables that are given here. So it so happens that some piece of code, in that piece of code, the method H of class A defines the variables U and W. And the method I of class A uses the variable U. Similarly, the method J of class A defines variable V, and the same method J of class A uses variable W. Method L of class A uses the variable V. Method method H of class B defines variable X, and so on. So on the left, we have a class inheritance hierarchy that talks about the variables of each class, what is their status access levels, the methods owned by each class, the descendant classes, their methods, which methods of the descendant classes override which methods of the parent class. On the right, we have a table which corresponds to the definitions and uses as pulled out from some code that uses the methods of this class. It says certain methods of certain class define certain variables. Certain other methods of certain classes use those variables. And remember what method overrides what method by looking at these arrows. Now there is an anomaly with reference to data flow definition and uses. So let's look at that. Look at the last bullet here. Suppose there is an instance of B that is bound to an object O. Okay, there's an object O and an instance of class B, which is a descendant class of A, is bound to that object O. And a call to the method D, the first method of class A, is made. Okay, now what will happen? Remember, methods of A are called in sequence. So D will finish running, it will call G. We are only focusing on the calls, we are not focusing on the code that is there within D. So D will finish running, D will call G, G will finish running, G will call H. But now look at it, the instance of object O is bound to, instance of B is bound to object O. So when H is called, A's version of H will not run, B's version of H will run. Is this clear? And if you see, B's version of H defines a variable X as per the table on the right. Keep that in mind. After that, B's version of I is going to run, and B's version of I is going to use that variable H. And then let's say you continue, K may be running, or B's version of A's version of I will run. Sorry, A's version of I will run, A's version of J will run, and so on, because they are called in sequence. But now if you see, for A's version of I and A's version of J, U and W need to be defined, which were correctly defined by the method A, by the method H in A, but they weren't defined by the method H in B. The method H in B only defined X. The method H in A was the one that defined U and W, which was needed by the method I to use. But now, because an instance of B was bound to an object O, the problem was B's version of the method H was executing. That didn't define the variables U and W. So when A's version of method I or A's version of J runs, the values U and W will miss getting defined. So there will be no values to use or incorrect values to use, and this will result in a data flow anomaly. And this whole thing happened because the object O was bound to an instance of B. Suppose the object O was bound to an instance of C, then similarly some other data flow anomalies can happen. Whereas if the object O was bound to an instance A, then maybe the definitions and uses will correctly happen. So we don't know whether which version of the polymorphic method will run. And because of that, certain definitions and uses that we might expect might not exist at all. So this becomes a big issue when it comes to object-oriented testing. So there is a useful graph model, call graph model, that is useful for visualizing these kinds of things. So let's look at the graph model. That's called yo-yo graph. As we just saw through the two examples, it's very difficult to understand which version of the method will be executed and which versions can be executed. So if you see here, for this example, method I, there is A's version, there's B's version, there is C's version. If an object O is bound to an instance of B, then maybe B's version will run. If an object O is bound to an instance of C, C's version will run. If an object O is bound to an instance of A, A's version will run. So 3 versions of the same method can run, but dynamically which version will run, we don't know. So the execution can bounce up and down in the class inheritance hierarchy. So such bouncing up and down, the calls in the presence of this is called a yo-yo graph. So for this class inheritance hierarchy example, let me first show you how the yo-yo graph looks like. Then we will come back and see the definition. So I've put the same picture on the left-hand side here without the arrows that talk about the methods overriding. But assume that the same method overriding happens here also. So there's class A with its 6 methods, class B with its 3 methods, out of which 2 methods override the corresponding methods in class A. Class C with its 3 methods, all 3 override corresponding methods in class B or class C. On the left, you have the method names to represent as the nodes of the graph. One row of methods per class. For class A, all the 6 methods are arranged in a row. For class B, the 3 methods are arranged in a row below the corresponding methods of class A. So H of B is kept right below H of A. I of class B is kept right below I of A. In addition, B has its own new method K that's kept separately. Similarly, method C, the corresponding methods are kept in a row below their respective overridden methods. So method I of C is kept below I of A and I of B. Method J of C is kept below method J of A. Method L of C is kept below the method L of A. Now let's look at the edges or the arrows. So there are 3 replicas of the graph. And they are arranged in layers, one for each class as per the inheritance hierarchy. At the topmost layer is class A, below it is class B, below it is class C, and the respective methods are lined up in rows. Those are the vertices of the yo-yo graphs. Now if you see, there are 3 copies and the yo-yo graph is slowly being built. The third copy below here is how the final yo-yo graph looks like. So let's look at the first copy of the yo-yo graphs. All the edges are present, all the vertices are present in all the 3 copies, but edges get built up as we move on. First one, there are edges that are boldly given from D to G, G to H, H to I to J. These represent the call edges, the call interfaces. So D, method D of A calls method G of A, method G of A calls method H of A, and so on. Now let's look at the second version of the yo-yo graph below here. If you see, in addition to the bold edges, there are edges that have these dashed lines. So method D of A calls method G of A, that's a normal edge. Then there is a dashed edge from method G of A to method H of A. What does this dashed edge mean? It means that take an object, if it's bound to an instance of A, then this dashed arrow call will be made. But if it's bound to an instance of B, like we saw here in this data flow anomaly, then H of B will be called, not H of A. So then the call goes down here. Once B's H is called, B's H is going to call B's I. After B's I finishes running, it will go back to the parent A's I method, which in turn will call J, and so on. So these second level represents yo-yo graph, which has little more number of edges than the first one. It has 2 kinds of edges, bold edges that represents the actual calls that will be made if an object is bound to an instance of class B, and dashed arrows represent calls that will not be made, but calls that exist, that could be made in other circumstances. Similarly, in the third level, C is where the box is enveloped in. So we assume that the object O is bound to an instance of C. So in this case, what will happen? D calls G, which calls B's H, which calls C's I, and then now the control will go back to B's I, A's I, and then C's J, and then B's K, and so on. And these dashed arrows here represent the other method calls that exist, but cannot happen in this case because the object O is bound to an instance of C. So this is what a yo-yo graph is. In a yo-yo graph, we have methods as vertices and edges represent method calls. Edges are further categorized into 2 kinds: calls that can happen and calls that will happen. Dashed edges represent calls that can happen. Bold edges represent calls that will happen. Which are the calls that will happen is dictated dynamically based on what the object binds itself to, and with other calls are those that can happen. So yo-yo graph is a useful way of visualizing class inheritance and method calls in the presence of polymorphic methods, just for visualizing so that we can understand what is happening. So look at the third bullet here. Yo-yo graph is defined on an inheritance hierarchy. It has a root, it has descendants. Root is the first method that runs. That is this method D. That is this method D. And then it has descendants. Methods, nodes of the yo-yo graph are basically methods. They can be new, inherited, and overridden methods for each descendant class, as we saw. Edges are basically method calls or call interfaces, as given in the source code. There is a directed edge from a caller to callee. That part is fairly clear. In addition, each class is given a level in the yo-yo graph, like we saw here, based on the class inheritance hierarchy. And it shows the actual calls made if an object has an actual type of that level. These are depicted by bold arrows, like here. The bold arrows and the bounding box says that the object has an instance of actual type B. Here it says actual type C. Then the calls to those respective methods are depicted by bold arrows. Dashed arrows are calls that exist, but at a particular execution, it cannot be made because of method overriding. This is what a yo-yo graph represents succinctly. So we just saw this. A's implementation, what calls what, which method calls what. Similarly for B, similarly for C. So at the top level, a call is made to method D through an object of actual type A. This is a simple, straightforward sequence of calls. That's this first graph here, right at the top. Second level, object is of actual type B. Then what happens? It started bouncing down to the hierarchy, down in the hierarchy to B. So the edges go down, method calls go up here, and then they start going down once again. At the third level, the object is of actual type C. So control proceeds all the way down to C, then comes back to B, then goes up to A, then comes down to C. So this expanding and collapsing control through layers in the hierarchy has the effect of a yo-yo toy bouncing up and down the thread, and that's why they've given this catchy name of a yo-yo graph. In simple terms, it's a call graph that represents method calls in the presence of class inheritance and polymorphic methods. Two kinds of calls are given based on whether object at runtime binds itself based on the actual type of the object at runtime. Those calls are given by bold edges. The calls that correspond to dash edges are calls that exist statically, but for an object of an actual type will not be made. And it's a very useful graph to visualize call graphs in the presence of polymorphic methods. So just by visualizing it, you will understand all possible calls that can exist given a class inheritance hierarchy. So I'll stop here for now. In the next lecture, we'll look at object-oriented faults and anomalies. Thank you.